Thanks, Jeff. What Jeff failed to mention was we lost 15-0. So, but we won our first 2 games, so we are in the playoffs. So it's a pleasure to be here to talk to you about future telescopes in space. And I'm going to talk to you about 3 telescopes. One, hopefully you've heard of, especially if you've been coming to these events for a while, the James Webb Space Telescope. The video that's going on the wall right now is actually showing when we had the scale model of the James Webb Space Telescope here in Austin in 2013. How many of you saw that out on the Long Center lawn? All right, a self-selected audience, I see. And so we'll let that play again. Actually, you know what? We'll just skip to the much prettier view here, so you can get a sense of how big this telescope is. So this is a full-scale model. You see people standing down there. They're admiring the telescope, but they're also there for scale. So you can get a sense of really how large this telescope is. Okay, so we're going to talk about this telescope. We'll talk about the science that it will do. But this telescope is almost old news. It's going to launch in 2018. Trivia answer right there. And so I'm going to talk to you about the next 2 telescopes that NASA's developing. One that really honestly will launch in the next decade. 2024 is the current estimate. And one that we're just in the earliest stages of planning for the decade after that, 2035 or so, maybe 2065. We'll see. We'll see how much money NASA gets. So let's talk about what is the James Webb Space Telescope. JWST is often referred to as the Hubble replacement, and that could not be farther from the truth. It is really the successor to Hubble, although Hubble is still working quite well these days, and assuming it can hang on for a few more years, it won't even be the successor. They'll both be up there at the same time, and so we can use them together. So how is it different? The reason why we need another one is that Hubble is great, but Hubble is small. The power of a telescope is in the diameter of its primary mirror. And the Hubble primary mirror is 2.4 meters in diameter. It's about the average height of your NBA center. And so that's sort of big, but for telescopes, that's kind of puny. On the ground, it would be nowhere near the largest ground-based telescope. So the James Webb Space Telescope, big advancement number 1, is going to have a primary mirror diameter of 6.5 meters. And so if we look at the total collecting area, the total area of the mirror, it'll be 7 times greater than that of Hubble. So it'll be 7 times more powerful. And so the images up there, I think somewhere I was handed a laser pointer, but I put it down to hold on to my beer up there. This is, anybody know what this image is called? Hubble Ultra Deep. I asked that same question in my class today. Hubble Ultra Deep Field. This is what happens when you take Hubble in all its glory and you point it at an empty region of space and you let it stare for a few hundred hours or so. And it's just filled with galaxies. But you'll notice it's not completely filled. There's lots of empty blank space in there, right? We have simulated what we should see if we do the same type of observation with the James Webb Space Telescope, and that's what we get on the bottom. And so I'll show you a zoomed in version of that in a little bit. The larger mirror is also going to allow the Webb to see a lot more detail. This is a real image of a spiral galaxy in the relatively nearby universe as seen with HST. You can tell it's a spiral, but it's kind of blurry. It's a little bit hard to tell the detail. And when we look at the same type of thing with the James Webb Space Telescope, we'll see all kinds of detail. And so we think we should see images about 3 times sharper than that of the Hubble Space Telescope. So that's all well and good. But that's not the biggest advance of the Webb. The biggest advance is that JWST is looking in the near infrared. And you might say, why do you care about the near infrared? Our eyes cannot even see at these wavelengths. And I will tell you, hold on a minute, we'll talk about that in a little while. Right now, I just want to tell you what the near infrared is. So this image here shows you the electromagnetic spectrum. And that is the range of wavelengths that light can have. And so our eyes are sensitive to the visible. Right here, this is where the sun emits the most light, so we evolved to be sensitive to that amount of light, and that's where Hubble is sensitive. But light can take a variety of forms, all the way from gamma rays through X-rays, ultraviolet. Here we can see a very narrow range, infrared, microwave, and radio. We can learn so much more about the universe by looking at objects in all of these wavelengths together. If we could only look in the visible, we would be very, very limited. The problem is, so you might say, okay, great, let's build a near-infrared telescope. Why do you need to put it in space? Put it in the ground, put it in West Texas at McDonald Observatory. We could go visit it, that would be great. The problem is the Earth glows in the infrared. Specifically in the near-infrared, the night sky is aglow. If your eyes were sensitive to near-infrared wavelengths and you looked up at night, the night sky would be glowing. And that's nice, you'd be able to see. But the problem is we're looking for these very, very faint, very, very tiny galaxies. And that glowing night sky is really a problem. And so we really need to go into space to have have the sensitivity to see really, really faint things. And so for the next few minutes, I'm going to tell you about some of the problems or challenges that JWST has had to deal with, or specifically how JWST will overcome these problems. And so the first challenge is the sun and the Earth. The sun is bright. Duh, right? The Earth is also pretty bright. In the optical, the Earth is reflecting sunlight. That's fine. So you might say, well, put a telescope on the night side. It won't be a problem. But in the infrared, the Earth is glowing. Just like the atmosphere is glowing, the entire Earth is actually glowing with thermal radiation. Okay? So the Earth and the sun are both a problem for an infrared telescope like JWST. And so our solution to this is to send JWST 1,000,000 miles away and have it hang out at what we call the second Lagrange point. And so this little simulation is going to show you where JWST is going to go. Here's the sun, here's the Earth, here's the moon. JWST is out here. This is not to scale, but it's about 1,000,000 miles away from the Earth. Okay. That would be awesome if it was to scale. Biggest telescope ever. NASA could stop. Mic drop. Okay, so here's L2. The reason why L2 is so good, you see this kind of weird triangular shiny thing here on the bottom? That is what's called a sun shield. That is blocking all of the light from the sun from hitting the awesomeness up here that is the telescope mirror and the telescope cameras. And the great thing about being at L2 is JWST can position both the Earth and the sun behind it. And so it can block the Earth and the sun with its sun shield at the same time. And so when the Earth is here, the sun is over here, JWST can look at everything on that side of the universe. Okay? As the Earth orbits around the sun, JWST is kind of following it, just like that, and it can see the other half of the universe. And so at any given point, Webb can't look anywhere because it's always looking away from the sun. It's looking at the half of the universe that is away from the sun and the Earth. But over 1 year, over one orbit, it can see the whole thing. Okay, so we have to send it to L2. We have to protect it from the sun and the Earth, but we've conquered that. It's a 7-layer sun shield. It will block all of that light from getting to the telescope. Challenge number 2, if I can get there, the fuel. JWST has to get to L2. Okay, it will get pretty much all of its velocity to get there just from its initial launch in a rocket, which we'll talk about in a minute. But once it gets there, it has to course correct a little bit to make sure it gets right into the exact right spot. And even once it's there, L2 is a stable point, but it's not completely stable. So it has to burn some maneuvering fuel to stay exactly where we want it to stay. Okay, so much like your car, JWST has a gas tank, and that gas tank can only hold so much fuel. And so if when we launch it and we send it out to L2 and it gets to the exact right awesome position, it will have enough fuel to stay there for 10 years. It's sort of the worst case scenario happens and we have to do a lot of course correcting on the way out there. It will have enough fuel to last for 5 years. After that time, we won't be able to keep it in position. We won't be able to point it very well. And while I have no doubt astronomers will come up with some way to make use of the telescope, much like they're doing with the Kepler telescope right now, it will lose most of its functionality. And so that's really the limiting lifetime. So that's not really a challenge we can overcome. That's it. We can hope that it gets there, hits it right on the target, and we'll have this telescope for about 10 years. And the question we commonly get is, can we send a robot out there with a gas tank to go fill it up? The answer is certainly technologically yes, but sadly the money is not there in the budget for that. Every time I go to the Space Telescope Science Institute in Baltimore, where they are in charge of this telescope, I ask, have you built the gas nozzle or the hole in the side of the spacecraft for the gas nozzle to go into? And the answer is still no. I'm still hoping maybe before they launch they'll do that, because then we can get another 10 years of a great telescope. So stay tuned on that one. All right, challenge number 3. This is the big one. This is the scary one. The size of the telescope. Big telescopes are great. Okay? Big telescopes are heavy, and big telescopes are big. Okay? So how do we get it up into space? Okay? The Hubble Space Telescope was launched inside of the space shuttle, which is great because number 1, we had space shuttles. Well, we still have them. They're just in museums now. And number 2, the Hubble could actually fit in the space shuttle cargo bay. Okay, it's big, but it's not huge. JWST is much larger. Okay, we don't have a shuttle, and it wouldn't fit even if we did. So what are we going to do? We're going to put it in a rocket, an Ariane 5 rocket specifically, and we're going to launch it from French Guiana, which is on the coast of South America here. It's a little bit hard to see in that image. And this is what's going to happen after it launches into space. It's going to be folded up all nice and snug. Once it gets up there, while it's flying out to L2, while it's flying 1,000,000 miles, it's going to do this. It's going to take 21 days to unfold from its compact little pocket that we put it into in the rocket to the point where we can actually use it. And so the first thing that's got to happen, the sun shield was all folded up nice and tight. It's got to unfold. Okay, this relatively thin foil screen now has to unfurl without ripping. Ripping's a problem. We don't want it to rip, so there it goes. It's got 7 layers, nice and slow. Take it easy, don't rip. The big thing, the scary thing, well, that's scary too, is the mirror. The mirror is not a nice circle, okay? Specifically, right now, there's not even a secondary mirror for the light to reflect off of to get to the camera. So right now, nice, expensive piece of junk. You'll see in a second, now we got our sun shield, so now it's a cool, expensive piece of junk because we blocked it from the sun. There's the secondary mirror coming down. And finally, the sides of the mirrors, or the ears, are going to fold out to give us our completed 6.5 meter, awesome $8 billion space telescope. All right, all of that's going to happen during October to November of 2018, after it launches, while it's flying out there. If it goes wrong, we cannot save it. We often joke about sending a grad student up there in the rocket with it to make sure it unfolds, and they'll get their PhD as they die in space. But that's not going to happen. There's sort of a mistaken thought that if there's a problem, we can send astronauts up there to fix it. But a couple of things. Number one, we don't have a space shuttle anymore. And number two, even if we did, the space shuttle and any spacecraft currently in operation by anyone in the world is only designed to go up into orbit. This is not in Earth orbit. This is out there flying off to L2. We cannot go save it. So we have to make sure it works. Okay? So how are we going to make sure it works? We're going to test the hell out of it. This telescope cost $8 billion to build. But that's actually a misnomer. It cost about $4 billion to build and about another $4 billion to test. When the Hubble Space Telescope was launched in 1990, did it work correctly? No, there was a problem with the mirror. You might say, how in the world could all the intelligent people at NASA launch a telescope that had a problem with the mirror? And the answer is they didn't do the end-to-end optical test that was necessary to catch this problem. And the reason why they didn't do it, anybody want to guess? Money. It was too expensive. Luckily for us, the Hubble was in Earth orbit. We had space shuttles. We could go up, put in the contact lens, essentially, and fix it. We cannot do that here, so we're not cutting any corners. We are doing the end-to-end optical test. It turns out that the James Webb Space Telescope is so big, the only building large enough to house it and do this optical test was Chamber A at Johnson Space Flight Center in Houston. So that's right, JWST is coming to Texas next year. None of you can see it. Probably not even we can see it. I'm still working on it. So right now, this is Chamber A. This is where the Apollo astronauts trained. Okay, it was designated a historical landmark. It was dirty. It was dusty. There were historical plaques on the wall. They had to rip it off. They had to clean it up. It's ready to go. They actually have a test version of JWST in there that they've been practicing on, and it will get on an airplane. This is ridiculous. They're going to take the entire mirror assembly, which is this part here. Okay. This is the primary mirror and the secondary mirror. It's not yet mounted to the spacecraft. The spacecraft is the actual thing that maneuvers it around. It's not yet mounted to that yet, but they will take this whole thing that's currently sitting, I'll show you a picture in a minute, at Goddard Space Flight Center, put it onto an airplane, mirror side down, fly it in the sky to Texas, land it safely, hopefully, take it out, put it in this thing, take a forklift, flip it over, do the test for however long that takes, take it back out, put it in an airplane, fly it to California, to Northrop Grumman, where it will get mounted on a spacecraft, and then guess what they're going to do? They're going to put it on a boat, send the boat through the Panama Canal, down to French Guiana, where they then fold it up, stick it in a rocket, send it into space. Nothing can go wrong, I'm sure. I guarantee you. All right, so those are the problems. Those are how we're going to overcome it. We're going to be optimistic. We're going to assume that everything's going to work fine, because if it doesn't, we all, at least everyone in this quarter, needs new jobs. Nobody told you that, sorry. NASA's never going to get another dollar for astronomy again. Doesn't work. All right. So let's talk about the science. So why do we care about light redder than your eye can see? And I'm going to give you a very biased perspective because I work on very distant galaxies. You can do lots of cool stuff with Webb for lots of things, but really the reason why this telescope was built was to study galaxies in the early universe. So this is a nice picture here of Edwin Hubble. This is how we all sit at work. We wear our tweed jackets, we smoke our pipes, and we stare very angrily into the cameras that are pointed at us. Hubble was famous for a variety of reasons, but one of them was for discovering that the universe was expanding. And so this nice little chart here shows the distance to galaxies on the horizontal axis versus their velocity. And what this shows is that a farther away a galaxy is, the faster it's moving away from us. And this tells us that the universe is expanding, which is great. Made a lot of people happy, except Einstein. This thing on the bottom, showing a guy getting hit in the head by an arrow, is really illustrating the Doppler effect. Okay, so the Doppler effect has to do with when a source is emitting a wave. If the source is moving towards you, the wave gets compressed. If the source is moving away from you, the wave gets stretched out. So you're most accustomed to hearing this with sound. Okay, if a train is going by you or an ambulance is going by you, you hear the pitch go up as it gets close to you, as the sound waves compress, and then the pitch goes down as they move past you. The same thing happens with light. Okay, so everything is moving away from us. Everything is being redshifted. All the light waves are being stretched out. Because more distant galaxies are moving faster away, that means that more distant galaxies are being even more redshifted. So we can take this to the extreme, and we can show that at a given distance, galaxies are moving so fast away from us that all of their light that we would normally see in the visible, that our eyes can see, it's all being redshifted into the infrared. These galaxies are literally invisible. If you look at them with your eye, and you had big 10-meter eyes, you would not see them. Or to make this a little better, if you looked at them with Hubble or the Keck telescope from the ground, you could not see them if you're using an optical camera. You have to use an infrared camera, specifically a near-infrared camera, to see them. So I'm going to introduce the concept of redshift. Redshift, or Z, or Z, if you're from England, is a number that we give to a galaxy to tell us how much its light is being stretched out. But redshift is really a time. If I'm talking about a galaxy at a redshift of 0, I'm talking about today. Okay, we are 13.8 billion years or so since the Big Bang. If I look at a galaxy at a redshift of 1, all of the wavelengths of light have been doubled. I'm already looking more than halfway back towards the Big Bang. So we're going to take it to the extreme. If we're looking at a redshift of 10, we are looking to within half a billion years, only 500 million years since the Big Bang. We're looking about 95% of the way back towards the beginning of the universe. And the most distant galaxy that has been found with Hubble, I will say at redshift 10, MC Heisey is going to talk about one at redshift 11. It's a little dubious. We'll talk about that. Hubble can see about redshift 10, and it doesn't do so well there. Galaxies at a redshift of 10, their light has traveled so long. Those galaxies were so young in the early universe. They're so small that we can just barely see them. And anything even more distant at higher redshift, all the light has been shifted to the near infrared. So if we want to study the earliest generations of galaxy formation and evolution, we have to use James Webb. And that's why it's being built. Exoplanets and stuff too, but we're going to talk about galaxies. All right, so question number 1. When did the galaxies first form in the universe? This is a super easy one to answer. Day 1 with JWST data, just look for galaxies at a bunch of different redshifts and see where do I stop seeing galaxies. Galaxies at redshift 10, check. Galaxies at redshift 12, check. Galaxies at redshift 14, check, hopefully. Galaxies at redshift 15, maybe not so much. That tells us about when the first generation of galaxies were forming in the universe. This is a range right now that we can only study on computers with computer simulations, which make awesome movies like these, but they kind of get to make up their own rules about what's going on because we can't observe it. They have no constraints on what's going on. Science case number 2, how did the first stars and galaxies affect the universe around them? Something happened at early times called reionization. The gas in the universe was neutral. That means all the friendly little protons had all their little electron friends. They were all nice and cozy. But once the first stars and first galaxies turned on, they blasted the universe with ultraviolet light, and they ionized that gas. We can see today the gas between galaxies is all ionized, and we don't know when that happened. We think galaxies did it, but we don't know for sure, and we don't know when it started. And that's really something that we're going to learn with the Webb. And so again, to give you a sense of what it's going to look like, here's our friendly favorite image. What's that called again? The Hubble Ultra Deep Field. I learned this in graduate school from one of my co-advisors. You always have to say Hubble Ultra Deep Field so everyone knows what telescope took it, as if any other telescope could take this image, but that's okay. The Hubble Ultra Deep Field, this is what you see with Hubble with hundreds of hours. If you spend the same amount of time with the James Webb Space Telescope, this is what you'll get. It's literally filled with galaxies. It's really hard to find a blank spot. There are blank spots, and that's why we need to build bigger telescopes. We'll talk about that in a minute. But we can see a lot deeper and a lot farther and a lot fainter. All right, so how's it doing? I've told you, when is this telescope going to launch? It's only 2 years from now. I used to love to think about this telescope. Favorite telescopes are one of my most favorite topics to talk about because they're in the future. You just get to talk about the good things. You don't actually have to start working and planning for them. The first proposals, if we want to use this telescope, we have to write a proposal that is competitively, it's a competition process where everyone, all astronomers write proposals and only like 10% of them get through. They're due next year. And so I'm going to go take my heart medication while you ponder that. Here's how it's doing. This gives you a sense of how close it is to launching. This is the clean room at Goddard. I took this picture last night at 11 p.m. while I frantically wrote this talk. It already looks like it's close to done. All of the primary mirrors are on there. They're black because there are covers on them so they don't drop a screwdriver on them. The secondary mirror is in place. It's almost ready to come to Texas. Maybe not now. It will float away in Houston, but maybe early next year they'll be ready for it. So it's going very well. So I'm going to spend the last couple minutes talking about what's next. So with all good luck, JWST will operate from 10 years starting in 2018 through about 2028. So what comes after that? And you might think astronomers are smart, and so the best thing we could come up with was, hey, let's build a 2.4 meter space telescope. Seriously, that is actually what we're doing next. And you might say, didn't we already do that? It was called Hubble. Okay, that is true. It is true that we are doing this, but this is a little bit different. This telescope is called WFIRST, or the Wide Field Infrared Survey Telescope. When you hear about it in the news, it will probably have a new name. We like to name our telescopes after famous astronomers after it launched, so hopefully this will have a nice name like the Vera Rubin Space Telescope or something else. But for now, it's a lame name called WFIRST. It's actually WFIRST AFTA, which is an even longer story. All right, funny story about WFIRST. Literally, it's actually a converted spy satellite. It's going to teach us about dark matter, dark energy, galaxies, and planets. We've always been planning WFIRST, but it was actually going to be a 1.3 meter space telescope, and it wasn't going to be nearly as powerful. But then one day, a few years ago, along came the National Reconnaissance Office and said, hey, we were cleaning out an old storeroom, and we found 2 Hubble-class telescopes, 2 2.4 meter space telescopes. We don't know why they're here. We don't know what people were using them for. But hey, NASA, we've got better things now. Would you like these telescopes? Seriously. So NASA said yes, of course. So we have taken them, and one of them is going to be called WFIRST. So why build WFIRST? All right, this is a schematic showing you the area of the sky that Hubble could see. The first 2 squares are 2 of Hubble's cameras, and the one on the right is JWST. Okay, this is actually already much enlarged, so they can see really, really specks. The width of the Hubble camera is the width of one of your hairs held at arm's length against the night sky. Okay, so this is representing that. Very, very small. What that means is that we only get a limited view of the universe, and we know the universe is somewhat clumpy. So when we do the Hubble Ultra Deep Field and we're counting galaxies, we don't know if we're looking at a clumpy region or an empty region. All right, and so that's why we built WFIRST, because in one shot, WFIRST will observe all of this here. These are multiple detectors. WFIRST will image this large region of the sky. And so I'll show you a quick video on WFIRST.
Telescopes generally come into 2 different flavors. You have really powerful big telescopes, but those telescopes see a tiny part of the sky. Or telescopes are smaller, and so they lack that power, but they can see big parts of the sky. WFIRST is the best of both worlds.
WFIRST is the Wide Field Infrared Survey Telescope. What I think of WFIRST as doing is building on what were the 2 great successes astronomically of the 1990s and the last decade. That is the Sloan Digital Sky Survey and the Hubble Space Telescope.
WFIRST is a NASA observatory that has the top ranking of the National Academy of Sciences
Hubble,
to
not
launch in the
WFIRST.
2020s. It has the same image precision and power as the Hubble Space Telescope, but with 100 times the area of sky that it views.
Looking at a large fraction of the sky allows you to get a more complete accounting. For example, the stars in the Large Magellanic Cloud.
So that's really key, the area that WFIRST is going to do.
So you can do
WFIRST is also going to, video should have stopped, so I will stop it myself. WFIRST is also observing in the infrared. It can do all kinds of great things for the distant universe. So what I'm most excited about is that right now we know of a handful of galaxies at redshift 10, maybe 5. And with Webb, maybe we'll find 20, maybe 50, I don't know. With WFIRST, we'll find hundreds, all of them brighter and larger and easier to study than what we'll find with Webb. But it gets even better. If we take a slight step back and look at redshift of 7, still in the very early universe, right now we know of 300 galaxies, and WFIRST will find tens of thousands. And so it's really going to allow us to map what we call the nodes of the cosmic web. Where are the densest regions in the early universe? So we'll make these excellent maps. And it's also going to do lots of really, really awesome stuff with planets. We like to make fun of planets because it's a really exciting area of astronomy, and it's not what I do. But WFIRST will find thousands of planets through microlensing, actually seeing a slight increase in a star's light as a planet passes in front of it and lenses the light and magnifies that star. WFIRST will also have what's known as a coronagraph, where it blocks out the light from a star so you can directly image the planets. And so this is a simulation of WFIRST looking at something like our solar system. WFIRST could directly image Jupiter a Jupiter-like planet and a star not all that far from our own. And so the last thing I want to talk about is what's next. WFIRST only works in the near infrared, much like Hubble. We can learn so much by looking at the ultraviolet. Anything about gas in the nearby universe or star formation in the nearby universe, we all need ultraviolet and optical imaging to do. One of the reasons why Hubble was so great is because it was a general purpose telescope. It had many instruments, it could do a lot of stuff. Okay, so we would like to build the true Hubble successor, and this is going to be called something that we don't know yet. And right now it has the ungainly acronym of LUVOIR, or Large UV Optical Infrared Telescope. There's a better name. There are a number of concept studies, and one of them is called the High Definition Space Telescope, or HDST. So we'll stick with that for today. And what could such a telescope do? It would be designed to find and characterize Earth-like planets. It would be something like 12 to 14 meters in diameter. So while WFIRST could image Jupiter around nearby stars, HDST, or LUVOIR, could image Earth around nearby stars. To give you an idea of how big it would be, here's our nice family picture here. This is sort of the small end, so it could be anywhere from 12 to maybe 14 or 16 meters. So the specific HDST design was 11.7 meters, quite large. Okay. Also good for galaxies, of course. I think building it to image Earths is a great idea. We're going to use it for galaxies, so don't worry. All right. Here's a Hubble image of a nearby galaxy, and here's what we'd be able to do with HDST. Your ability to resolve minute details increases with an increase in your telescope mirror, and so we can learn a lot about how galaxies form and evolve. We can learn a lot about gas around galaxies by looking in the ultraviolet and looking through gas around galaxies. One of the cool things we've learned with Hubble is that galaxies have these huge gas envelopes which have all kinds of hydrogen gas and even metals that have been kicked out of the galaxy due to supernova explosions. But we're limited. We can only do this by looking at the brightest background objects. With a 12 or 14 meter space telescope, we could use puny little galaxies themselves as flashlights to illuminate what we call the circumgalactic medium around galaxies. And finally, we could see all of the cosmic web. This is really what the universe looks like. We can't see this with our puny telescopes and our puny eyes. We can see it in simulations. When we look with Hubble, we see maybe the brightest galaxy here. And when we look with Webb, we'll see a few more. But if we build a 12 or a 14 meter space telescope and launch it into space and look at the universe, we will see all of these interconnected filaments and really get an awesome view of the universe. And so the bottom line here is stay tuned. We've got a lot coming up, and by we, I mean NASA, and by NASA, I mean you, the American taxpayer. Okay, JWST is launching in October 2018. I'm sure we'll be doing lots of events around that launch when it happens. WFIRST, only 6 years later, hopefully in 2024, and HDST, a very approximate 2035. Thank you.
So for the record, I call Redshift Z because you give me that look whenever I say Z. So we have one question from Twitter, which is, how does JWST orbit the Earth while staying outside the Earth's path around the sun? Is there math involved?
There is definitely math involved and physics. So it's not technically orbiting the Earth. It's orbiting this point called L2. So as Earth, see, here's the sun. My beer is the Earth. As the Earth is going around the sun, I can't do this. UV JWST. Follow the Earth. As the Earth is going around the sun, follow the Earth.
Well,
it's kind of going like this. There we go. It's going like that. Does that work? Yeah, sure. That works. So it's not actually going around the Earth in a circle.
Yeah, and there is math involved. I think I could do that at one point. I can't now. Okay, any other questions for the Notorious L.A.E. back here?
How are you going to fit that HDST? How are you going to get the HDST into space?
We'll have to fold it up twice.
Could you repeat the question, please?
I mean, we'll have to fold it up twice. I mean, I'm sure rockets could get a little bit larger, but unless we have some breakthrough in technology, we're still going to be using chemical-propelled rockets. So it's going to have to fold up. Or for a really advanced civilization, we could build it in space. Space.
Down the front here.
Two quick questions. Do you always get estimates
of the lifespan of things, and we always beat them, and you gave a fuel estimate. Is that a hard number, or is that something we might end up 15, 20 years ago?
Yeah, that's a great question about the mission requirement and actual mission duration. So the mission requirement for the Webb is 5 years. It's got to last 5 years, hell or high water. There are enough redundancies unless something catastrophic goes wrong. It should last 5 years. As for the 10-year deadline or the 10-year timescale, I'm honestly not sure. My sense from talking to people is that that's pretty accurate, what we think in terms of the fuel will be gone. But certainly NASA has had a pretty good success rate. Hubble's been up there for 25 years. I actually don't know what the initial time estimate was. The difference with Hubble is it's been repaired 4 times by astronauts. And so even if it runs out of fuel after 10, or if it doesn't run out of fuel after 10 years, maybe something breaks. There are a lot of moving parts, so we don't know.
And how safe is that rocket?
So the great part about the rocket is that is the contribution by the European Space Agency. And so they're launching it into space, which means they get access to the telescope, and I think that means we get to blame them if something goes wrong and make them build another one. I was actually looking at this last night. I think that rocket has launched 57 times and never had a problem.
Okay, one in the middle over here.
Yeah, so what kind of detectors? So these are infrared detectors. These are a little bit different than the charge coupled devices that are in optical cameras and kind of like what's in your phone. So they're infrared detectors. There are, I'm going to mess up, 4 instruments on the James Webb Space Telescope. I think I removed my backup slides, so they're not on there. There's a near-infrared camera called NIRCam, a near-infrared spectrograph called NIRSpec. We're not so good with the names. A mid-infrared imager called MIRI, and this thing called NIRIS that's being built by the Canadians that will also do spectroscopy. And so we'll have 4 excellent imagers, and right now we're working on the ability to use 2 at once. We do this all the time with Hubble. When one camera's looking here, the other one can look here, and so why not use 2 at once if you can? Fun fact about the Hubble, can anybody guess how much memory the Hubble can hold? So if you take images with Hubble, how much memory do you think it can hold? It's in gigabytes, so it's not so bad. Raise your hand if you think it's more than 20. And raise your hand if you think it's less than 10. All right, from my tone, you already know 2 gigabytes. I came up with this awesome survey until they said, no, you can't do it. You would take data way faster than you can actually download it. Webb will be a little bit better, although not a lot better.
Okay, we're out of time, so we're just going to do one more question down front here.
This thing, as it's going around the sun, is still basically on a plane. 360-degree plane.
Yes.
Does it have the ability to turn, say, 90 degrees and see other things other than what it's just pointing at?
Yeah, great question. So I said it's always pointing away from the sun. Not technically. So the sun shield, imagine the sun is back there. The sun shield is sort of blocking out this half of the universe behind me. But I can look anywhere. I can look up, I can look down, I can look left, right, and out. So there are actually 2 points called the north ecliptic pole and the south ecliptic pole where JWST will be able to look all the time, straight up and straight down. The rest of the regions it can look for sort of 4 to 6 months at a time.
Okay, let's say thank you very much to the Notorious L.A.E.